All right, this is section 4.2 paired data. And the idea with paired data is that we know there's a dependency based on observation. Okay, so usually when you are looking at data, and suppose I have a couple of columns of data. So this kind of goes with the idea of the sample mean and so forth. So I have some numerical data, and but suppose instead of just one column of data, I have a couple columns of data. So, column 1, column 2. Well, what I usually assume, if I'm trying to compare these two columns, and so the idea would be that I have that's what's causing the two columns would be some sort of categorical variable. That, then when I have some, x1, x2, x3 data here that are numerical, and here, some y1, y2, y3. My assumption is that all these observations are totally independent of each other. But that's not always the case. Sometimes the data are paired data. And their first example in the textbook where, and I'll kind of simplify it down, they want to look at the price of textbooks at a bookstore and on Amazon. And so here, so if we're going to look at those data, so one was the UCLA bookstore and the other was Amazon. Okay, well, you see, this, we have a categorical variable of location or store place or name of store or organization. How about organization? So our categorical variable here is the organization. Okay. And so you might assume things are independent of each other when I look at these observations, except each observation is, so if I go here, observation 1, then observation 2, then observation 3, UCLA here, if I'm looking at their data, it says 2767. I don't know what book that is. It's not our books. This is some old data, but 27.95. Well, what I'm going to, let me erase this stuff here. What I'm going to do is actually say, oh, this was book 1, and then book 2, and then book 3, and so forth. Well, I would expect if this is a particular book, these two prices should be pretty similar. And because it's the same book. And, on the other hand, another book, now, I'll use their numbers, 40.59 and 31.14. And I'll go to book 3 here, 31.68 and 32.00. These, this is another book, and so I would expect their prices to be similar. Now, it's pretty amazing. They're two very different. I mean, to me, they seem very different in price, but, the other two books don't. But I would expect those data, if I were to plot UCLA prices and Amazon prices like this, if I were to look at that plot, I would expect for each and every book that, here is like the y equal x line, say. I would pretty much expect to see data falling along that line like that. Now, it could be it's mostly under or over, because what would it mean to be under a line? If I have something like this, it says Amazon is cheaper. If I have a point up here somewhere, it says the UCLA bookstore is cheaper. Okay, so I might expect one of the two to have more dots, kind of either under the y equal x or over the y equal x, depending on which one I think might be overall cheaper. But nonetheless, I really expect those data to fall along this line. So I expect that by observation number here, these data are highly associated by observation number there, and so to say that this column is independent observations from this column, not true at all. I mean, there is a definite association going on here, and so we have to try to take care of that. And the method we use, okay, our method is pretty darn simple. Okay, so I have two columns of data that I think are paired. So, column 1, column 2, x1, x2, y1, y2, and these are the observations. What I do is I just make a third column of, and it doesn't really matter, either C1 minus C2 or C2 minus C1. I'll just say C1 minus C2. I'll make that column x1 minus y1, x2 minus y2, and so forth, xn minus yn down here somewhere. And now what I'll do for a hypothesis test or a confidence interval is I will use method from 4.1 on C1 minus C2. Okay, so I don't use a new method. If I think the data are paired this way, as in the case of, like each observation is a different book, but I would expect the price of a book to be about the same, then I should, I know I have dependent columns to start with, and so I should do this subtraction technique, and then I use the method from 4.1, so I can get a confidence interval. I would get a confidence interval by taking from this column. I'll call these W's, so W1, W2 to Wn. So what I would do is I would take W bar plus or minus my Z alpha over 2, or, well, actually, I should use, because it could be a small sample, I'll use T. T alpha over 2 of my n minus 1 degrees of freedom, and then times my standard error. And, I would get that standard error the same way. I would, so this would be W bar plus or minus T alpha over 2 n minus 1 S of W, the standard deviation, the sample standard deviation, divided by the square root of n. Okay, so that would be my confidence interval. My hypothesis test. Now, in this case, the null hypothesis, well, so typically what I want to know is there a difference in the price, right? That's their initial question is, well, is UCLA cheaper or Amazon cheaper? Which one's cheaper? And so they look at this difference, and well, if neither one is cheaper, if they're basically the same, then the difference should be 0. And so for the hypothesis test, the null hypothesis is always for one of these paired tests that, well, always, typically, unless you have a reason to, you want to know if there's a difference of 1 or a difference of 10 or something like that. But typically, you would say that mu is equal to 0. And then your alternate, if it's a two-sided, would be that mu is not equal to 0. And so, since mu is equal to 0, when we create our test statistic t, we would, take our, and I'll call it W still, W bar, okay, the sample average there, or sample mean, minus mu, okay, but minus 0, so you don't really notice it, and then divided by the standard error. So this becomes our sample mean divided by our standard error, which is our sample standard deviation, divided by the square root of n. Okay, so that's our t statistic that we would use, and we would check that probability using a t-table and the correct degrees of freedom and so forth. So here I'll put a n-1 for our degrees of freedom, and we would use that t statistic as we did from section 4.1, and so that's it. I mean, that's how you would do it. Some definite cases that come to mind are typically before and after. Okay, because I might, and it might be working with people, it might be using some treatment on some sort of object or something to see if it holds up better. But, typically I might have a before and after, and so a very usual thing is, to assess effectiveness of something, so I do a before assessment, on each. Now I'm going to say participant. Now it could be an inanimate object, but I'll say I'll do a before assessment on each participant in a study. But typically that's the way it works. So I do that. Then I that assessment has some sort of numerical score. Then I give a treatment. Now that treatment could be a review for an exam in a class. It could be a particular presentation. It could be a medication. It could be a therapy of some kind, all sorts of different things. But I give some sort of treatment. And then after that treatment, at some point, I give an after assessment. On each participant. And so these definitely look like they ought to be paired, right? I would expect that if a participant had a low score, whatever that means, that could be good or bad, but a low score to begin with, then after the treatment, I would assume they would still have a low score or a lower score than other people if I'm calling it low. And similarly with high scores or medium scores or something like that. And so you want to look for those kinds of things. You know, do I think I have paired data, or do I not? Okay, and so if I do, and again, you know, before and after is something, but the first example they give is not a before and after. It's the same book. You know, what makes something common here? It's the same book at two different stores. Okay, so this is all, though, that's going on in the case of paired data. It's not a new technique or anything like that. It's just if it's paired data, I use these, you know, same confidence interval, same sort of hypothesis test. Now, the big thing on the hypothesis test is our mu of that difference is always 0. We're assuming there's no difference in the data, and then we're going to look to see, do our data support there being a difference, right? Mu is not 0, or do they fail to support that? So they fail to reject the null hypothesis, okay? But it is exactly those same techniques from 4.1. And I think that's really all I probably need to say about this. So if you can perform the test in 4.1, you can perform the test in 4.2. As soon as you come back here, as soon as you find the difference in each observation of those two columns of data. But once you do that, you treat it as a column of data and go from there. Okay, so that's good, I think, for 4.2.